Okay, this is a video looking at the refraction of light, and we're going to deal with this in moving not just from one medium to another medium, but also from two different refractive index mediums. Anyway, a little bit of theory first, and then let's build it up from there. First of all, let me draw in a medium and a ray of light that's coming in. And I hope you know from your knowledge of GCSEs that we always reference the angle to the normal. And the normal is very simply just something at 90 degrees to the surface. And then we draw in, then we have another light beam. Okay, now the reason why it bends towards the normal, as you can see that's bending towards there, is due to a change in speed. In actual fact, it slows down. Normally we reference these change in speeds compared to the speed of light, because here we say let's go from air into something like water or glass, therefore we go from a speed that's the speed of light to something that's slower. So most often we talk about, let's say this from air, and the velocity here is 3 times 10 to the 8 meters per second. Good. And then we have the velocity in which is going to be less than the speed of light. Okay, good. Right. Let's go for a bit of algebra to explain how and why that is. Okay, I have here a beam of light which has a width, finite width, and I'll draw in the two normals. And here is my incident angle, which is the same for both of them. And this is my refracted angle, which will be the same for both of them. Now, the light up until this point here at right angle, those 2 points there, are doing absolutely the same thing. They're identical. Similarly, the light from here to here, onwards in that direction, is doing the same thing. We have wavelengths of this light, which are coming in, and then we have wavelengths going out. And notice here, there is a compression in the wavelengths. So the wavelength here decreases compared to the wavelength there. The speed as well is decreasing compared to the speed here, but the frequency is the same. I think that's probably worth mentioning because it's the same colour. Okay, let me take another colour and highlight these two triangles here. One triangle there and the other triangle there. Now that area we are going to draw in large so you can see what's going on inside there. Whoops. Let's go back to the pen. Okay, then so I have this triangle, this right angle triangle here, and I have a right angle triangle here. And I know that the distance there is the speed times by the time period, whereas the distance here is going to be the speed, which is the velocity multiplied by the time period. The time periods, of course, are the same here, but the velocities are not the same. So that's why we have a longer length and a shorter length. Let me annotate that. C times T, V times T. I also know that this angle in here is I. That is a right angle. This is a right angle. And therefore, as a consequence, that is refracted angle R. If you don't believe me, then just take a while to look at these angles inside here and see what's happening. But those are correct. So very simply, we have a nice sign identity that says, if this is my opposite and my hypotenuse, sine I is going to equal the opposite over the hypotenuse. And similarly here, sine r is going to be opposite over the hypotenuse. Over the hypotenuse. Good. I'm going to rearrange these to make h the subject. And of course these are identical, so I'm going to equal them together. I'll do it in another colour. So therefore I'm going to swap these terms around and then equal them. So Vt over sine r is equaling h, but of course that will equal this as well. So therefore we have Ct over sine I. Take some time to appreciate that. The t's obviously cancel, and that leaves me with a general expression, and I'm going to move this up to there, swap those two round, which gives me, I'm going to write it somewhere in a bubble over here, sine I over sine r is the same as c over v. Good. Now, I'm going to make one little small amendment here. The ratio of the speeds is equal to the ratio of the refractive indices, n2 over n1. This material is n2 and this material is n1. The ratio of the speeds gives rise to this quantity called the refractive index. So therefore I'm just going to modify this a little bit and say it's equal to, oops, problems again, n2, n1. Okay, so there is my proof. Right, let's go to another page and just write down that proof again. So this is my n1, sorry, this is, I've written that wrong. Okay, this is n1 and this is n2, two different refractive indices. And I have light coming in and bending towards the normal. So therefore we can say to ourselves that we know that n2 is greater than n1. It's probably worth noting. And the big equation we're using is sine I over sine r is n2 over n1. The way I like to memorize this is I like to say, okay, sine I over sine r is the inverse. It's going to be n2 over n1. So this over this is the same as that over that. Excellent. Okay. Let's try some simple readings with this first. Okay, let's try n2 equaling 1.5 and n1 equaling 1. Okay, first question is first. What angle, if we have this inbound at 30 degrees, what is going to be refracted angle r? And then also, what is going to be the new velocity? Okay, if you think you know the answer, hit pause, otherwise here comes the result. So, let's start with sine I over sine r, n2 over n1. I'm looking for r, so I need to do a bit of rearranging. Sine r is going to be equal to sine I over n2 times n1. I've moved this up to there, this down to there, and moved that up to there. Okay. What next bit do we do? Well, we say r is now going to equal sine to the minus 1 of sine I of n2 by n1, giving us, let's substitute the values, sine 30 over 1.5 by 1, giving us, and that gives us 20 degrees. Okay, and what about the velocity? Well, let's just work that out over here. The velocity is going to be c over v is n2 over n1. So therefore c over n2 gives us v, because I know this is 1. That gives me 3 times 10 to the 8 over 1.5, because this you obviously know is the speed of light, 3 times 10 to the 8. If you don't, remember it. And that gives me 2 times 10 to the 8 meters per second. Wonderful. Okay, now let's try another one. Okay, this time we're going to look at the movement between two refractive indices which are not air, which do not include air. So, let's say again we have 30 degrees. This time I've got 1.4 into 1.5. Okay, what's the refracted angle R? Well, if you think you know the answer, hit pause, otherwise here comes the results. Sine I, let's write down the identity first. N2 over N1. Sine R is going to be sine I over N2 by N1, therefore R is going to be sine to the minus 1, N2 by N1, and that gives us sine 30 over 1.5 by 1.4, whoops, sine to the minus 1 of that, inverse sine, got a bit carried away, and that gives us 28 degrees. Okay, so this is looking, hopefully this is making sense, and any rearrangement of this equation obviously will hold true. So just keep memorizing the idea of that change in refractive index. Now, as a little aside here, it's probably worth noting that this could be written as, because we're moving from the one material to the second material, we call it 1n2. And that identity might be worth noting down, that the 1 goes below, the 2 goes above, and this n is just the ratio of the two of them. It's just a different way of describing it, really. Right, time for another problem. What about if we had, if we're now looking at moving from a more dense medium to a less dense medium? Let's imagine we're going this way around, and we have a ray of light that's refracted away. Now, that's all well and good. Let's just do the sum, shall we? Just get an idea to start with. Now, this matters. Let's say n1, n2. Now, this does matter which way around you write these, but keep memorizing here. We have sine I, sine R, n1 over n2 this time, because I is down here with the same 2, so I go this one over that one gives me that one over that one. Or indeed, we go from 2 n1. This entire ratio gives us, well, I need to plug some values in first. Let's say I'm going from 1.5 to 1.33. It's definitely bending away from the normal, which we've seen, that's good. And therefore, let's give it another, I like using 30 degrees because it makes the sine identity so straightforward. Okay, and we're going to try and use this notation this time round. Okay, so that gives us 1.33 over 1.5. That gives us 0.887. So we're looking for the refracted angle again. I'll do this nice and quickly. R equals sine to the minus 1 of, I've moved that up to there, this down there, give us sine I over 2n1 sine to the minus 1 of sine 30 over 0.887. And that gives us 34 degrees. So there's not much movement here. It doesn't bend quite as much. Okay, let's remind ourselves of the critical angle. How does the critical angle work? The critical angle happens when this moves to a position that the refracted beam is at 90 degrees, and this we call the critical angle. So let's do it again. Sine I over sine R equals n1 over n2, which is the same as n1, 2. So therefore this tends to 1 because it's a 90 degree angle, and sine 90 is 1, so we can get rid of that. And we're looking for and at that point this therefore becomes the critical angle. So what do we need to do? Well, therefore theta critical is sine to the minus 1 of 0.887, giving us 62.5. That's quite large. That's quite a significant angle in order for this to happen, because it's going from such similar refractive indices. Okay, so some problems then. Okay, we're going to make this one a little bit more different, using a different idea. This time we're going to move from, let's just raise that, let's go from this direction to that direction. And what I'm going to look for here, what I'm going to tell you, sorry, is that we have 2.8 times 10 to the 8 meters per second and 2 times 10 to the 8 meters per second. And what I want to know is what is the critical angle between these two. If you think you know, hit pause, otherwise here comes the answer. Okay, we do the same again, but this time sine I over sine R gives me n2 over n1, but we know that this is that identity is right. In other words, that the ratio of the refractive indices gives us C and V. It's almost the inverse. So therefore it's no good writing this and putting the speeds just directly into there. I need to invert the speeds. This will be V1 over V2. Good. Again, I know the refractive index is, the refracted angle will be 90 degrees, hence this becomes 1. So therefore that leaves me with sine theta critical is going to be V1 over V2, which is 2 times 10 to the 8 over 2.8 times 10 to the 8. Forget about those bits. Therefore theta critical is going to be sine to the minus 1, 2 over 2.8, which gives me, should be 45.6 degrees. Okay, bear that in mind, this inversion of the speeds. But otherwise, I hope that's all made some sort of sense. Right, to really test you, here's the last one. The question is, with a block of glass that's running at n equals 1.5, I shine some light, and I'm trying to shine it to get it through the corner. If I'm working to air, can I get the light to pass through, even deviated, can I get it to pass through the corner? And, so let me just write that down. Can light pass through the corner? And if the answer is yes or no, what would happen if, so that's the first bit, and the second bit is, what would happen if it were water? Glass were in water. Okay, if you think you know the answer, hit pause. Otherwise, here comes the solution. Okay, part A. Now, what I want to do is, if this was coming in steeply, it would be bent steeply. So the best chance I've got at going through here would be a very, very shallow angle. What would happen if I was coming in at 89 degrees? In other words, if I were coming in at that angle, then, in effect, this would be the critical angle. So, what is the critical angle? Well, theta critical is going to be sine to the minus 1 over 1.5. If you want to take time to work that out, please do. And that gives us an angle of about 41.8 degrees. Good. Now, here is my right angle triangle. And my question is, what is this angle here, theta? Theta, of course, is going to be 180 degrees minus theta critical, minus 90, which gives me 90 minus theta critical, which is the same as saying 48.2 degrees. Now, 48.2 degrees, theta is greater than theta critical. So what's going to happen is, in all cases, the light will bounce back. So the answer is simply no. Light will always bounce back, because even at the steepest angle, at the critical angle, it's greater than the critical angle, so therefore it bounces back. And anything like this will be even greater than the critical angle. The question is, what happens if we surround this with water? Part B. Well, theta critical, this instance, will be sine to the minus 1 of, and if you looked up water, you'll know it's 1.33, so therefore 1.33, oops, get that one, 1.33 over 1.5, and it has to be that way round, remember, of course, because this can only be on something smaller than 1, and that will give us a critical angle of 62.5 degrees. Now, if we do the same again and said, what's theta going to be? Well, it's 180 minus theta critical minus 90 gives us 90 minus theta critical, which is in effect 27.5 degrees. So this angle here now is 27.5 degrees. And because the critical angle is 62.5, this is well lower. So now it's much less than theta critical, and so therefore, yes, light is able to pass through, though deviated, pass through the corner of this glass block. Okay, I hope that all made sense.